Hello everyone. So far we have discussed about the wave equation of vibrating string or a rope and vibrating helical spring, and we also discussed about wave equation of cylindrical bar when a projectile hit the bar from one end, and also we discussed about the wave equation for unbounded medium or infinite body. In these discussions, so either we took a simple wave shape or we did not explicitly mention the shape of the wave. So now in this lecture we want to discuss, we want to derive the general solution of wave equation for a general shape. So, so what we learned so far is for vibrating string, so the equation we had is second partial of y with respect to time is equal to v square second partial of y with respect to x. Similarly, for spring we had these equations. For cylindrical bar, hitting with a projectile, second partial of u with respect to t is equal to k rho and the longitudinal wave velocity for infinite body or unbounded media. Medium is second partial of dilatation with respect to t, lem is constant, lambda plus twice of lem is constant, mu divided by mass density. So these are the expressions we had for these different cases. So for vibrating string and spring, we assumed sine shape, and for other cases we did not explicitly define the wave shape. This is just implicitly accepted that the square of the velocity of the pulse was given by the parameter that relates the 2 second partial derivatives. So now in this lecture, so we will find the general solution of this equation. So general solution for waves of general shape. So we know that the partial differential equation equations of the form A double partial with respect to x, B double partial with respect to x and t, plus C double partial with respect to t, plus dot 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 equal to 0 are classified into hyperbolic when b square minus 4 ac is greater than 0 and parabolic when b square minus 4ac is equal to 0 and elliptic when b square minus 4ac is smaller than 0. So, in this case, in the previous slide whatever equations wave equation we took, so that can be rearranged to write in this way: c naught square double partial of u with respect to x2 minus double partial of u with respect to t is equal to 0. So, here A is c naught square if we compare with this equation at the top, and b equal to 0, then c equal to minus 1. So, obviously if we see b square minus 4 ac is equal to 4 c naught square, because c naught is the wave velocity, but anyways this is square of the c naught and that should be positive, and that means this equation, or if we write in the other form, c naught square double partial of with s this equation is hyperbolic. So, hyperbolic equations can be solved, partial differential equations can be solved with two ways. One is separation of variables, and the other one is transformation or method of characteristics. So, this is appropriate for mostly for standing wave, and this is appropriate for travelling wave. So, standing waves are combination of two waves that moves in opposite direction. Suppose we have a fixed wall and we have a string, and then we are trying to move the string with a string like this, and if you want to try to move the string up and down, so the wave will go forward, like first this portion will rise and then this portion will rise and then this portion will rise. So, this is travelling wave, but in case of standing wave, if we have a wave like this, and then if this wave reflects back from the other wave, and due to constructive and destructive interference, the wave forms something like this, where these are called nodes and these portions are called antinodes. So, basically this standing wave it does not look appear like it is moving, but this is travelling wave. In case of travelling wave, this happens generally when only one wave travels, and we can see the wave travelling from one side to other. But in the standing wave, it happens because of the constructive and destructive interference, and this is two waves are involved. In this case here it is, one is the incident wave and other is the reflected waves, and we cannot see the waves moving from one side to the other side. So, what we will do here is we will use the separation of variables method for this general solution of the wave equation. So, for separation of variable, so the solution is generally look like this if you use a multivariable function of x and t. So, we need to separate out the two variables with these two functions capital X and capital T. So, here for standing wave so we can have it like this, u naught sine of n pi x divided by L cos of n pi c naught by t by L, where L is the called characteristic length and c naught is wave velocity. So, we have separated the variables. So, now from the relation, trigonometric relation sin A cos B is equal to half of sin A minus B plus sin A plus B. So, from this relation we can write the above expression sin n pi x L cos n pi c naught t divided by L is equal to half of sin n pi by L x minus c naught t plus sin n pi by L x plus c naught t. So, ultimately if we express the displacement u x t, so this will be like u naught by 2 sin n pi by L x minus c naught t plus u naught by 2 sin n pi by L x plus c naught t. So, we can express the displacement in terms of two different functions of the variables x and t. We can generalize the above equation by assuming two functions which are actually non-harmonic functions, which are not harmonic. So, let us say f and z x plus c naught t. So now we have the two variables. So, variable is first one is x minus c naught t, and the variable 2 is x plus c naught t. So, we will verify whether these two variables, these two variables will provide a correct solution to the equation, solution to the wave equation. Solution to the equation. So, for that we want to substitute these two variables with a substitute this is x plus c naught t and eta x minus c naught t by substituting these with two variables. So, now we can express the differential of the multivariable function du. The differential we can write it as du and from that the partial of u with respect to x will be we can express it like that. From the above, from these relations, what we can get is the partial of those variables with respect to x will give a value equal to 1, this will be 0, and the second variable will also be 1. So, both of them are if we take partial derivative with respect to x, that will give us 1, and then we want to have the second partial of displacement with respect to x. So, what we will do is now differentiating u with respect the partial of u with respect to x, that is nothing but the partial of u with respect to the two variables we defined. And if we differentiate once again, so this will be partial with respect to x and which can be again written as So this will give us plus 2 so this is one expression for second partial of u with respect to x. Similarly, we will do for second partial of u with respect to t. So for that we have partial of u with respect to t will be so from our definition of the variable x minus ct, so the partial derivative of this variable with respect to t will be so this will give c naught, and partial of the second variable with respect to t will give us minus, this is minus c naught, which will give us minus c naught. So this will be 0, and then we want to have our partial of u with respect to t, that is c naught minus c naught partial of with respect to the second variable, or we can write it this way. U. So second partial of u with respect to t2 will be equal to c naught which will be equal to c naught square partial of u with partial of u with respect to the first variable, partial of u with respect to the second variable, and this will finally give us an expression like c naught square minus twice second partial of u with respect to the first variable and the second variable, plus second partial of u with respect to the second variable. So this is what we got for second partial of u with respect to t. So now we will use both these relations. Like first relations we got this, let us say it is a second partial of u with respect to x2, and the second one, let us assume this is b. So from a and b, if we substitute in the wave equation, and the wave equation will be C naught square. So wave equation, so the wave equation we have is C naught square, this is equal to second partial of u with respect to x. So now we will write the wave equation from a and b using the relation we got an a and b. So that will be something like this, twice plus this is second partial is equal to C naught square plus second partial of u with respect to second variable. So this was our wave equation, the original wave equation. So now here this all terms will cancel out except the middle terms. So this will give us second partial of u with respect to both the variable is equal to 0. So this is the wave equation in terms of these two variables, which is equal to, we assumed as x plus c naught t and x minus c naught t. Now what we assumed is the general solution is f function, the first variable and the second variable and the first variable. So now to arrive at the equation, to arrive at this wave equation, let us say we write as C. To arrive at C, we will just verify, we differentiate this, let us say we are writing d with respect to our two variables, okay, and we will see whether we end up with that equation. So first we are differentiating with our one variable, and which will have a we can write it as f prime, and then if you differentiate with the other variable as well, which will be equal to 0, that means the general solution is we will write it in the other phrase. Oh sorry, so I made a mistake here. This C naught square should be on the right hand side, C naught square, that you must have noticed that this was a mistake. So the general solution of the wave equation for a general shape can be given by u, a function of x and t can be given by c minus t z x plus c naught t. So, physical meaning of this equation is function f and function z describes the shape of the wave or pulse, describe the shape of the pulse, and f in the positive x direction and z in the negative x direction. So, and wave, that is pulse, that is wave velocity is c naught. In this case, wave velocity is c naught, and f and z, these functions describe the shape of the wave, and the shape of the wave is unchanged with time. Shape unchanged with time t. So, if we draw a general solution for a uniaxial stress, so for a uniaxial stress, if we draw the shapes, let us say this is positive x, this is negative x. So, for uniaxial stress, general solution of wave will give, let us say in the positive x direction, the wave shape is something like this, and this is, let us say, this is travelling towards this direction, and this is, let us say, time t equal to 1, this is a time t equal to 2 and time t equal to 1. So, this is actually represented by f of x minus c naught t, and in the negative direction, that wave is shape will, let us say, it will be different with, this is time equal to t1, this is time equal to t2, and the function z will define here, define the wave shape c naught t. So, this is the solution of general solution of the wave equation for general shape. So, next we will discuss about the elastic wave in cylindrical bar, which we have already discussed, but there are some additional considerations that we will be discussing in the next lecture. Thank you.